Okay, so what I want to talk about today is kind of a mix of things centered around what are called decision trees. So in a broad sense, today's lecture would be like decision trees, and then a couple of things towards the end that are called bagging and boosting. And so this is a very simple idea, right? So it's a nice kind of breezy beginning of the week kind of thing to talk about, right? So this is an extremely easy way to design a classifier, and with some simple modifications, decision trees can actually have very competitive performance to some of the more complicated mathematical stuff that we've been talking about so far, right? So let me just ask, show of hands before I start, who has done decision trees like in a CS course or something like that? Like some quarter of the class has done it, right? So the idea is very simple. So the idea is kind of like, not that much different than an amped up version of 20 questions, right? So it's like, 20 questions. So what we're going to do is we have some data, right? So let's suppose that we have data that is, again, like X's and O's. And again, one thing about these X's and O's is that it's not very easy, or in this case, it's not possible to design a linear separation between the X's and O's, right? At least not in this feature space, right? So instead, what decision trees are going to do is it's going to be something like this. So first it's going to say, okay, at every branch of the tree, I'm going to make a choice about what variable am I going to branch on, and then what is the threshold for that variable. So for example, here, I just have like two features, x1 and x2, right? So it may be that the first decision that I would make would be to say, okay, I'm going to draw a line here, call this position theta 1, and I'm going to ask, is x1 less than theta 1, right? If the answer is yes, I take this branch. If the answer is no, I take this branch, right? And so let's suppose that I'm in, the yes branch, right? So I say, okay, well, now I'm over here. Now if I want to try to separate the data better, I could say, okay, is x2 less than this number, right? So now my next branch over here looks like, is x2 less than theta 2? And then maybe I say, okay, is x1, after I go through this yes-no branch, if I'm less than, so if I'm below here, then I say, okay, is x1 less than theta 3? At this point, the way I've drawn these red boxes is that everything has its own, like all the x's and o's are separated, right? So I can say, okay, well, if that's true, then here I would decide x. If it's not true, I would decide o. If I decided it was above the line, I decide o here, and if I decide like this, right? So this would be a way of basically taking sequential divisions of the space. And the way I've drawn it here, I'm dividing the space along the coordinate axes, right? So I'm making a choice about x1 or x2. And then I'm done, right? So this here basically is called the root node. And then these guys here are basically what are called leaf nodes. And at every leaf node, I make a decision, okay? And so the goal is basically at every stage of the game, I should be making a binary yes or no decision that reduces my uncertainty in the label after I make the split, right? And we're going to quantify what that means in just a minute, right? The way I've drawn this, it's what's called a binary tree, right? Which means that I'm making a yes or no decision at every node, right? It doesn't have to be like that. For example, I could say, is x2 in the range blah, 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 or blah, 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 blah. So I could have like a three-way decision. But all of that just reduces down to a binary tree in theory anyway, so it's easiest just to draw a binary tree. Now, the way I've drawn this is a classification problem, right? Meaning that we're looking at binary x's and o's. It doesn't have to be binary. It could be like multiple classes, right? And also, this could also apply to regression, even though I'm not going to really talk about regression today. One way you could think about this is saying that, I keep on doing this, and every box I have a different regression model that I train, so that I'm basically having an individual decision that gives me a continuous valued number inside every one of the boxes, right? So instead of being a class, I get a number, right? So let me just write that down. So this also kind of applies to multi-class situations or also regression. And so that's it. Now, the other nice thing about decision trees in general, it's frustrating me that this is like somehow like not square, but what are you gonna do? The nice thing about decision trees in general is that they lend themselves to situations when you can't even kind of quantify what the features are, right? So here, for example, we're used to dealing with everything we talked about so far, numerical features, right? But kind of one kind of side note is that, also this kind of idea works for kind of non-numerical features. Right? So for example, suppose that I'm trying to classify different kinds of fruit, right? So I could say something like, the size of the fruit, I could just kind of have these bins that are like small, medium, and large. And then I could have, shape could be, round, thin, spiky, something like that. And I could have taste be on the range of sweet or sour, and so on, right? So the idea here is that I don't have to put numbers on, like round equals 3 and spiky equals 5, because there is no natural numerical like ordering of those kinds of features anyway. But I can still build a decision tree that basically says at every section, okay, so is the shape, spiky or not? If spiky, go this way. If not spiky, go that way. So it's the same kind of idea, and the same theory applies without having to have anything that's numerical at all, right? So it's kind of nice in terms of a very generalizable algorithm, okay? And so the question is, what is the best way to draw this tree? Because obviously, at every stage, I have many possible decisions to make. I have to choose which dimension am I going to split on, and then given that split, what number am I going to choose to draw the line at, right? And so you can imagine that this is kind of like a computationally complex problem because it's like explosive and combinatorial, but there are some good heuristics for how to do it, right? And so today we're going to talk about a well-known algorithm called CART, which stands for Classification and Regression Trees. Not very clever acronym. And we're really going to focus on the classification side. And I am going to restrict myself just to make it easier to numerical features and splits, just because it's easy to do that. Now, there are other types of trees that apply kind of more or less the same kind of theory. So if you're doing any sort of reading, you may find out about like, other methods that are called like ID3 or C4.5, right? Some really clever names here. So basically, these are other types of methods for splitting trees, right? So again, what is the advantage of applying a decision tree? Well, the nice thing is that you can imagine that you could design any boundary that you wanted, right? So if I'm making kind of constant splits on the axis-aligned boundaries, you could imagine that I could create a very kind of squirrely, tree that looks like this, where this is all like class 0 and this is all class 1, right? So my decision boundary can be kind of arbitrarily complicated by making these kind of axis-aligned little lines, right? And so while it may take me lots of branches to make that very detailed decision boundary, it's something the decision trees are able to do, right? So obviously for kind of, conciseness, we want to make the most kind of compact, fewest splits decision tree that we can to avoid having like an overcomplicated tree, okay? And so that's what I'm going to talk about today, is this CART heuristic for making a decision tree, okay? So let's talk about it. So the idea is, suppose that we've chosen a node, okay? So suppose we fix a node n, right? and want to determine a feature query, let's call it T, that makes the data, or makes the descendant nodes as what's called pure as possible. Right? So purity basically is a measure of how much of the data is all in one class, right? So for example, suppose that I'm making my very first decision and I've got like X's over here and O's over here, right? So before I do any split, this data is mixed 50-50, right? So it's like as confusing or as uncertain as you could get. Once I draw the line here, then both of the left side and the right side are 100% pure one way or the other, right? So that's kind of like the idea, is that we want to measure kind of how good is the split based on, after we do the split, how pure are the left and the right nodes, right? And so this should remind you of like, kind of Fisher's discriminant type stuff, and there is kind of a connection to that, but you don't even need anything as fancy as that to do decision trees. It's actually much simpler than that. So all we really need is a measure of what does pure mean after we do the split. And actually, the way it's defined in decision tree theory is actually a measure of impurity instead of purity, but it's the same idea, right? So all we need is a measure of impurity at a node n. And we're going to call that measure Q of n. And so it's not too hard to think about what would be good impurity functions, right? So, and there's, again, it's your choice what you'd use for such a function, so I'm just going to give you a couple of common ones, right? So some common impurity functions. So one is called the entropy, right? So there's called the entropy impurity. So who has heard of entropy as a mathematical concept? At least a couple people. So yeah, I don't know if I talked about this when I taught probability. I mean, I'm sure it came up in passing. But basically, the entropy is kind of like a mixture. It's a kind of a measure of how unstructured is a distribution, right? So here, that definition is the following. So if I have k classes, I have this function, where here, this is the fraction of data in the kth class. Right? So for example, suppose that I have entirely certain classes, right? In that case, the probability of one of the classes is going to be 1, and the probability of all the other classes is going to be 0. So that means that I'm going to be multiplying, a bunch of zeros together, and the entropy is going to be 0 because there's no uncertainty at all in that decision. Whereas if I had the classes be uniformly distributed, right, then the probabilities would all be the same, and my probability would basically look like, log of n, however many classes I have. Well, I'll write that down in just a second. Let me write this other one down first, then we can talk about it for a second. So there's also a thing called the Gini impurity. I'm assuming it's a soft G. And that's even simpler. That's like saying I just sum up over all the classes that are not equal to each other the fractions like this. And so the key concept for each of these impurity functions is that when the data is, when the classes are uniformly split inside the node, that's like the worst case scenario, and the impurity is highest, right? And so when the data is all from the same class, then the impurity is lowest, right? And we want to maximize the purity, which means we're minimizing the impurity, right? So if I think about it, that's like saying, let's consider, two classes, right, to make it a more, direct. So if I have the best case scenario, that's like saying that class 1 has exactly 1 probability, class 2 has exactly 0 probability. Then if I apply these measures, well, both of them are going to give me 0, right? Whereas the most uncertain case is like saying that the probability of the classes inside the node is equal to 1/2. And in that case, these give me slightly different numbers, right? This one would give me, the entropy one would give me log 2, and the Gini one would give me 1/4. So the scale is a bit different, but the whole point is that if I think about the proportion of class 1, that both of these cases have a picture that kind of looks like this, right? Where it's, minimized at the endpoints where things are certain and maximized in the middle where things are uncertain, right? So that seems like a pretty reasonable measure. Questions or comments about how this works? Pretty simple. There's also something that you could use that is called the misclassification impurity, just as a side note. So you could call it the misclassification impurity. There, it's basically saying I take 1 minus the maximum probability. So again, that's like saying that, if I chose something that wasn't the maximum class and it was wrong, how bad could it be, right? So it's like if I have certain classes, again, the maximum probability is 1, this number is 0. If I have uncertain classes, then the maximum is no bigger than 1/2. The problem with this one is that this is not differentiable for what it's worth. Not that we have to take a lot of derivatives anyway, but generally we often in machine learning prefer cost functions that are differentiable, and these are nice and smooth. They have this nice picture. This one is more jaggedy, okay? And so the way it works is we basically select a impurity function that we care about. I think that the Gini impurity is fairly common, but again, doesn't make a huge difference, I don't think. And so the idea is that, if we choose, a feature dimension at node n, what is the best S to split at, right? So it's like kind of saying, if I go back to like this very simple picture, I've chosen, okay, I'm going to split along the x-axis because clearly it seems better than splitting along the y-axis. Now I'm choosing where do I draw this line. Obviously I want to draw it in the place that has the best impurity, right? I don't want to draw it over here because that doesn't do anything for me. So how would that work? Well, I just have to have a measure that says we choose the location with the biggest decrease in impurity. That's like saying that what I look at is the before and after, right? I have my before impurity, and then I subtract off, if I draw the line, now I have basically a new fraction of points on the left node and the impurity there, and a fraction of points on the right node with an impurity there, right? So here, this is basically like, the fraction in the left or right node. And then these are the resulting impurities that would happen if I were to split at that node. And so if you are like an information theory person, which probably not many of you are, but just as a side note, so let me just say that if Q is the entropy impurity, This is what's called the information gain. Provided by the query. And there may be many values of this S that would give you the same quality. So for example, here I can see that there's a little bit of wiggle room with, I could draw this line probably anywhere in a certain range, and I'd get the same impurities at the leaf nodes. So in that case, you just like average the S's that are going to give you the best one, right? Draw the line right down the middle. And so again, this is not that really different than the way you'd play a game of 20 questions in normal life, right? Every time you're trying to ask a question that will reduce your uncertainty as much as possible, right? You're not going to kind of chip away at the edge of your query. You're going to try to split those classes right down the middle to ask as few questions as possible, right? So this kind of quantifies, if I told you what dimension that I wanted to use, what would be your value of S? That still kind of raises the question about how do I choose which dimension to use at every step? And in that case, honestly, you probably could just do an exhaustive search over all the dimensions and pick the one that gives you the best, right? So, how to choose what dimension to split on, a simple answer is just do exhaustive search and pick the best one. And this is what's called a greedy algorithm. Show of hands on who's heard of a greedy algorithm before? Right, so yes. So basically what that means is that you may be making the choice that seems like the best right now, but there's no guarantee that if you had the power to look ahead 5 levels, that you could have done something that seemed less optimal at the time that would have paid off for you more later. That's just the way a greedy algorithm works, is that you're kind of looking at short-term gains, right? So it's not always the optimal thing, but it's very easy to implement. Otherwise you have to kind of do all this look ahead, right? So you also need to have a way of deciding when do I stop splitting, right? So, when to stop splitting. Because, honestly, you could, if suppose your data was really, really intricate, you could keep on splitting down until you've drawn a super precise boundary around the X's and O's, but that would be a classic case of overfitting the training set, right? So you may sacrifice 100% accuracy on the training set for having a more compact decision tree, right? So let me just say that, if I go all the way, then fundamentally what you have is a lookup table, right? Because you're putting every point in its own little box, right? Which doesn't make a lot of sense. So that's extreme overfitting. So there are, by now you should probably be able to guess what are some reasonable ways that we could do this, right? So some reasonable things we could do are cross-validation, right? So we don't use all the data at once. We separate the trained data set into a fold of, stuff to train, and then a validation data set, and we do that several times so that we're not using all the data all at once, right? You could have basically a threshold on how much I improve at a node, right? So if I'm kind of seeing negligible improvement or improvement below a threshold, I eventually just stop splitting, right? You could also have kind of I would call a MDL or BIC type criterion. In case you don't remember what those mean, this stands for minimum description length, which I'm not sure we actually even talked about. And BIC is something that you did on one of the homeworks when we were fitting the Gaussian mixture models, right? So it's kind of like saying you have one term that's how good is the fit, and then you have a penalty that says how many parameters did I use, right? So you guys did that at some point to choose how many parameters should be in your Gaussian mixture model, right? The same kind of idea. It's like saying, okay, the more splits I add to the tree, the more I penalize the tree, right? And then you could also have something that's more of a statistical argument. You could have statistical significance of the split, kind of with a more probability type argument that says that if the data is distributed in a certain way, by chance, you may, see the data like this and like that, it's a random process. So you could have some sort of like, was making this decision likely to statistically improve the outcome, right? So those are all like kind of reasonable things that you could do. Let me stop and ask questions or comments so far. Okay, so one problem in general with this type of system is that, since you aren't able to kind of like look into the future to see what might be good to do, you may have a heuristic that stops splitting at a leaf too early when it might have been better to keep on splitting even though it didn't seem immediately productive. You could have done better if you had gone a few more levels into the tree, right? So, common issue is that, splitting rule might stop too early, although, future benefits could be gained. And this is what's called the horizon effect. Since you're only really looking one step ahead, you don't know how much better it could get. So one common alternative in the tree world is kind of the other way around. It's called pruning, right? So an alternative to this kind of greedy algorithm, or not an alternative to this question of when to stop splitting is what's called pruning, which again is like a metaphor for trees, right? The idea is that you grow out the tree fully, like you just blow out the tree until it's fully done, and then you start to trim away nodes that don't matter, right? So in some sense, you're growing the whole thing, and then you're snipping away parts of the tree, right? So it's like saying that maybe my decision tree is some sort of like, super complicated thing, blah, blah, blah. I have different levels like this. Sorry for this poor illustration. But then after I grew the whole tree, what I may do is say, actually, I don't need this node. This doesn't really add anything. And maybe I don't even need this whole branch, or maybe I don't need this whole branch, right? So you kind of like build it out and you start to chip away, right? So that's what's called pruning. So pruning is basically saying I grow out the whole tree and then I basically merge pairs of nodes to make a smaller tree. So basically, I will merge a whole bunch of nodes that have a common ancestor as long as the change in the impurity is not too large, right? And so there are methods that you can do like every leaf node at a time, or you could, like I kind of drew here, just take off whole chunks of branches, right? So if you were a CS person, you can imagine there's all sorts of like super exciting computational complexity type of arguments you could make for how to grow, how to prune, right? This is like an algorithm person's, dream, right? So I'm not an algorithm person, but that I can imagine there's a lot to say, right? So now that I got into this, I'm just curious, does this look familiar to CS people? Have you seen this in a different way? Show of hands. I thought this was like kind of an algorithms like kind of, thing. Anyway, well, if you haven't seen it yet, maybe you'll see it again. So how could we do better here? So there are a couple things. So one is that the way I describe this is that, suppose I had a situation like this where the classes were actually nicely separable, but not along the coordinate axes, right? So a decision tree would probably do here would be to make some sort of like fine stair-steppy kind of division that would get me good classification, but would require me to make like a whole bunch of tiny decisions, right? Whereas if I were to apply like PCA, like we learned last time, right? I could draw this line that would evenly separate the classes, the difference being this line is not axis aligned, right? So one thing that you could do at the cost of increased complexity, there are a couple things, right? So if we were to, we could do better if the lines aren't axis aligned. Right? So one possibility is, I could pre-process the data set by doing PCA. And then I arrive at kind of like this rotation of the coordinate axes from the old to the new. So for example, PCA on this data would kind of turn this data around so that I could draw a straight line on the x2 axis and it would be great, right? So one option is to do, PCA first. So pre-process using PCA to discover important axes. And in fact, I think that's what I asked you to do on homework 4 is the data set, I don't remember what the dimensionality is. It's like 400 or 500 dimensional or maybe even 700 dimensional. And if you do PCA, first of all, you should find out that you only need to have 100 and some coefficients to have 95% of the variance in the data set. Once you rotate the data set into those PCA coordinates, then you can do a decision tree on that 165 dimensional data, and that should be fine, right? So that's a lot more efficient than doing all 768 dimensions at once, right? The other thing you can do instead of PCA at all is just to allow an arbitrary linear classifier at each stage. And so, for example, let me just show something here. Oops, no, not you. No, again, not you. I know you can't see what I'm doing anyway, so it doesn't matter. Yes, this. So here's just an example that shows that, if I were to be forced to classify this data using axis-aligned decisions, then the top figure is kind of what I would get, right? Which is not that bad. But the bottom figure, this is basically the same data that shows if I could draw diagonal lines instead of straight lines, that then I could just basically draw 2 diagonal lines that would separate the data fully, right? Now, this also is kind of indicating that this would be like the split and merge problem, right? So what I could do is maybe I would end up having to grow this tree fully with a bunch of lines, and then I would cut away until I found out that really all I needed was this top line and this line, right? So that's one issue. Again, you can imagine that would work, except that it would be more computationally complex, right? And also, this kind of diagonal lines does imply that you have numerical values. You can't do this with like spiky and round fruit, right? You can only do it with numbers. So that's one thing. The other thing I wanted to show you is that decision trees are known, and this is actually the other picture I was showing you, right? This versus this. But this is the other picture I wanted to show, which is that decision trees are known to be very sensitive to the data, right? So for example, here's some data, 16 data points, and all I'm doing here is I'm changing this value of 0.36 to this value of 0.32, right? That's what this asterisk here is. So if I just change that one data point a little bit, I get very different decision boundaries for the classification tree. Let me make this a little smaller, right? So that means that the tree is very sensitive to just little changes in the data, right? And generally, we don't want to have classification that is so sensitive just moving one point around, right? So that's one problem with decision trees is they are kind of fragile. So what can we do about it? So let me just write that down first, which is that, in general, trees generally are very sensitive to the training points. Just changing one point location can have a big effect on what that tree looks like. So this is called instability. So what can we do about it, right? So this is leading into the other kind of main topic of today, which is a couple of cool statistical approaches that, again, are very simple, called bagging and boosting. And so this, again, was something that caught on quite a lot, kind of, I guess, in the maybe like late 90s, early 2000s, when people realized that you could take a whole bunch of a whole bunch of like marginally good classifiers, like better than chance classifiers, but not amazing classifiers, and kind of combine them all to give you an uber classifier that would be much better than any of the single ones combined, right? So, you know, kind of a key idea here is combine a bunch of what are called weak classifiers, into a stronger one via some sort of aggregation. And I'm going to talk about two methods called bagging and boosting. And the overall stability of the bagged or boost classifier will be a lot better than any single classifier alone. So again, these are extremely simple ideas, right? So bagging is simple. So suppose we have n training samples in our data set. We take k draws of some subset of these samples from the data set. And from that small sample, or train a set of classifiers from C1 to CK, right? So that's like saying, suppose I had 50, training sample points. On each try, what I might say is like, I'm going to make 5 classifiers. On each of the 5 classifiers, I'm going to take 30 of my 50 training points. And I'm just going to train my, unstable decision tree classifier on just those 30, right? So now I've got 5 different classifiers at the end, right? And then what we do is just take the majority vote. So we take the majority vote of the K classifiers as the final decision. Right? So if one of the classifiers says number 2 and one of the classifiers says number 3 and 3 of them say number 4, then I choose number 4, right? It's just like majority vote of what the classifiers say. So that's kind of a cool, simple way, just in the same way that kind of like from probability and statistics and signal systems and so on, that if I have a bunch of averages of the same draw of a random variable, that for example, some of those numbers the average of those numbers has lower variance than any one of the numbers originally, right? So it's kind of like saying that, each of these classifiers in a probability sense is like an IID draw out of the data. And so all the classifiers themselves have the same expected value of their classification performance, but since they're all basically independent, I average them together to reduce my variance, right? That's the same kind of idea that's going on with bagging. So super simple idea, okay? Questions on that? Okay, so bagging, been around for a long time. Boosting is a kind of a smarter idea, which is saying that instead of taking just random sample sets, I kind of prioritize my sampling to deal with the cases that seem to be most complicated, right? So boosting is a smarter way of adaptively sampling or adaptively selecting the kind of like most misclassified points at every stage. So I'm kind of like adaptively choosing which points should I use to train my next classifier are the ones that the first classifier had a hard time with, right? So for example, let's suppose that I have 3 data sets. Say I have a data set and I want to train 3 classifiers, right? So what I may do is say, okay, suppose I take, I take a third of the data, let's call it D1, and I train classifier C1, okay? Now that classifier may be kind of crappy, right? I didn't use much of the data, and I'm only using, one classifier. All this classifier needs to do is be better than a coin flip, right? Better than random chance, right? So then what I do is I select D2 to have, half the points that were correctly classified by C1 and half the points that were incorrectly classified. So that's like saying that now I've got a coin flip for C1. It doesn't know what to do with these points. So now I train C2 on that set of points, okay? So now I've got two classifiers, right? So now what I could do is I could say, I'm going to look and see, like, where do C1 and C2 disagree? I'm going to choose a subset of points where they're not giving me the same answer, right? So then I could say, select, D3 as points where C1 and C2 disagree. And then I train some new classifier C3. And then I kind of have this hierarchical decision of saying, like, okay, so, if C1 and C2 agree, then choose that label. Otherwise, choose, the majority label of these three, right? So I'm kind of being a little bit smarter about, like, forcing the classifiers to adapt to the places where they're making mistakes, right? As opposed to just kind of like randomly sampling. So here, the difference between boosting and bagging is that boosting, I'm making non-independent decisions at every stage, right? So bagging is like every classifier has the same expected performance. Boosting is a little bit different because the classifiers depend on each other in this kind of hierarchical way, right? So that typically does better. And so the kind of upshot for both bagging and boosting for both things is that, the key idea is that, this whole ensemble of classifiers, this is sometimes called an ensemble classifier, will have lower training error than basically any of the component classifiers. So the ensemble is better than any of its parts, and it's also better than a single classifier on all the data. Meaning that this idea of kind of like not trying to train on the whole data set at once, but training on sampled pieces of the data set and allowing for more generalization is a better thing to do, okay? And so one very popular boosting technique, which I'm going to just say in algorithmic form here, is called ADA boost. Or I guess maybe more sense called ADA boost, but I think of it as ADA boost. So a popular boosting algorithm. And let me just be clear that boosting is a general term for this kind of like adaptive selection, right? But ADA boost is a particular example of a boosting algorithm. So a popular boosting algorithm is called ADA boost. At least that's the way I say it. And so the idea here is that, it's a little bit confusing in the boosting example that I gave to think about like how does this generalize to like 5 classes or something like that, or 5 classifiers, right? Not super obvious like what the pattern is. ADA boost is a simpler idea, right? So the idea again is to say that I'm always drawing some samples and I'm trying to, at every draw, focus in on the samples that are currently having a hard time with, right? So like the ones that are good, don't try to pick those guys because I already know how to do those pretty well. Pick the ones that are not so good. And so in a sense, what's happening is that every sample is going to have its own weight, and I'm going to sample according to those weights, right? So the idea is to kind of like sample according to, points that were badly classified last time, or badly classified so far. Okay, so let me write down, since I've been not very mathematical today, let me write down actually one mathematical algorithm here. So here's the AdaBoost algorithm. So basically, the first thing I do is I initialize for every, so I have a setup is that I have, xi comma ti points for, n data samples, right? So basically, I guess the way I'm drawing this is like, feature vectors, and then these are the targets, right? So these are like the classification labels, right? So what I'm going to do is I'm going to initialize weights at every stage. First of all, I'm going to initialize them as just even probability, right? So I guess it's like saying, I have initially equal weights. And then for k equals 1 to some maximum number of iterations, I train a weak learner. Just think about some sort of analogy, right? Where you're all weak learners, but you could power together to be some sort of uber learner, right? We should see about how that goes on the exam. I should take like an average of all the yes or no questions on some exam and see how well the majority work. I'm not calling you weak, don't get me wrong. So anyway, train a weak learner, CK, using D samples according to the PMF WK, right? What this is like saying is that, WK is like a probability of picking that point in my sample, right? And so initially, I have an equal probability of picking, all the points equally, right? So now what I'm going to do is I'm going to say, let's let the error equal the training error of CK on this data set. And now let's let alpha k equal some function of the error. And don't worry too much about the, form of this function. It's just what they use in AdaBoost. The kind of basic idea, though, is that if I have a low error, then I have a high alpha, right? So now what I'm going to do is I'm going to reweight the points by e to the minus alpha k if this is a correctly classified point, and e to the plus alpha k if this is incorrectly classified. And I normalize everything to sum to 1. Right? So it's very easy. It's like saying that, okay, I see how well my classifier did, right? If the error is big, then this alpha number is low. If the error is small, then the alpha number is high, right? And then what I'm going to do is for each of the points in my data set D, I'm going to change their weights where if it was correct, I'm going to make that weight smaller. And if it's incorrect, I'm going to make that weight bigger. And so immediately after the first iteration, a bunch of the points are going to have non-uniform weights, right? And so now my next draw will prioritize the points, or will favor the points that were not great in the last bunch of iterations. And this keeps on going. So basically, after I do a bunch of iterations, it kind of depends on which points get selected, which draws. But eventually, the ones that were no problem kind of fade away in the sampling, and the ones that are close to the decision boundary get sampled all the time, right? So it's a clever way of doing things. And so then how do I kind of finalize my decision? So the final class is I basically threshold, the sum of the weighted, classification results. right? So it's like saying, each of the classifiers kind of has a quality of how good they are. And so the alpha k kind of keep track of how much weight they should have in my final combination. So I kind of have like a weighted score of all the classifiers, and then I take the best, right? So I guess the way I wrote this is kind of like more of a regression thing than a classification thing, but I could also say I take the majority vote of something like this, right? So in practice, this is very effective. When AdaBoost came out, suddenly everyone realized that this could take somewhat crappy, decision trees and turn them into really good boosted classifiers. So in practice, this is definitely worth looking at. And so that's bagging, boosting, AdaBoost. The last thing I want to say about this kind of thing is something called random forests. So random forests at the time were, again, a super popular, easy and effective way of doing classification that was very appealing because they were so easy to train and they worked so well. So I want to say just one slide on random forests, which is basically, specifically for trees, a certain way of doing bagging. It's like basically a modification of bagging, specifically for trees. And the reason I say that is that, in theory, the boosting and bagging that I talked about before could apply to any sort of classifier that you had, right? Could apply to some just like crappy linear classifier, right, that doesn't do very well, but does okay, right? So you don't have to have a tree to do any of this stuff. But random forests, because it has forest in their name, like it's a bunch of trees, right? So it's kind of like a very simple idea. So the simple algorithm for random forests is for k equals 1 to the number of trees, I draw a sample of some number of training data points. I grow a tree to the data by, and this is the critical part, selecting D of the capital D dimensions at random, and then, picking the best, variable split among the D. So kind of the critical idea here is that I'm not allowed to choose all of the dimensions of the variables all the time. Instead, I'm restricting my attention not only to a subset of points, but also to a subset of dimensions. In that way, the classification is basically the trees are no longer correlated with each other, right? Which is kind of like a statistically important idea, saying that we're trying to basically separate these trees to make them as independent as possible, right? Or as uncorrelated as possible. So, here, this D that I choose, could, for example, be like, some very, low dimension, or even, just choose one dimension for a given tree, right? So each of these trees is pretty dumb, right? And then again, the classification is just the majority vote among the trees. So kind of the idea is that you're forcing the dimensions to be different every time, which means that when I'm choosing the best split, I'm not always going to take the same dimensions because I may not have them accessible to me at a given step. And so this works surprisingly well. And again, this is super easy to implement compared to something like a support vector machine, right? Like I could have taught this on day 3 of class without any math at all, right? It's just a very easy idea to just keep on dividing up your data. And so again, random forests were once very, very popular for regression and classification. And I definitely wrote papers about them early in my career that worked pretty well, right? So that's why I think it's interesting to compare your results on homework 4. You've got the kind of like, neural networks decision trees and nearest neighbor. So decision trees and nearest neighbor are both conceptually much simpler than neural networks, but you probably should find that on that simple data set that they are competitive with neural networks. Like, it's not like the decision tree performance is going to be like 30%. I think it will probably be whatever, 70 or 80%, right? So the lesson there is that you shouldn't throw away the old stuff just for the new and hot neural networks, because the old stuff still can work fairly well for some simple problems, right? And again, if you are programming on some sort of like resource constrained machine, then maybe you want some sort of like simple if-then structure to implement a classifier, much easier than having your classifier do like some sort of a nonlinear optimization, right? Okay, so questions or comments about this? Yes?
I have a question about sort of like boosting and
yeah.
So you mentioned that the idea is you take a bunch of weak classifiers. I think in the context of like trees specifically, like what exactly does that mean, like a weak classifier? Because I think in the beginning of the lecture we talked about we can let the tree grow very large, and that could really, like, you can really get 100% of the training data set. So I'm wondering, like,
yeah. So what is a weak? So a weak classifier, I guess the way I would say it, doesn't have to be much better than a coin flip, is one way to think about it, right? So suppose I'm doing binary classification. I could try to design, by growing the tree to a great depth, a classifier that had like, 99% performance, right? Which would be a strong classifier on the training data, but it would be probably way overfit, right? Instead, what I could do is I could say I'm going to train my decision tree to get like 55% accuracy, which is not that much better than a coin flip, but then I train 20 of those things and I boost them, right? That's the kind of idea, is that not every one of the classifiers independently needs to be great, and I can save time in growing each independent classifier by not waiting until it's super good, right? So that's kind of what it means. So this is the key idea, is that a weak classifier is not meant to be the best thing that I can do, right? Yeah. So again, it's kind of like a little bit of a paradoxical idea, is that you don't try to make every one the best that they can, you just try to get them to be good enough, right? And that will save you time in the long run. Yeah, and honestly, I'm not 100% sure on how that works, but I think that you would basically say, okay, at the point where you design a stopping rule or a pruning rule, that's where you kind of let your preferences be known in terms of how good do I want each of these things to be, right? So you could say, okay, I want these to be like 60% classifiers. I'm going to merge nodes until they are at that level, and then each of the trees or whatever is a much more compact object than if you let it grow like super long, right? But yes, I'm not an expert, but I think that's the idea. Yeah. Other questions or comments about this stuff? Okay, so to compensate for today's pretty breezy lecture, I'm going to give you a heads up that Thursday's lecture is going to be a little bit more intense. We're going to talk about hidden Markov models, which is kind of like one way of thinking about data that depends on previous estimates in time, right? So far, nothing we've talked about is kind of treating these samples as anything other than IID samples from some distribution, but lots of signals like music and speech and so on are clearly things where you're building up a signal over time and samples are correlated with each other, right? So hidden Markov model is one way of applying machine learning to temporally correlated data. And so that's going to be on Thursday.